Well, good morning and happy Friday. So I'd like to look at ion exchange today, and we'll look at briefly some theory, but we'll mainly focus on the application of ion exchange. Dr. Davies is going to cover ion exchange in 481. So what I will do is I'll post a link to his lecture so that if you want more on the theory of ion exchange, you can take a look at that video. So just in terms of thinking about where we can use ion exchange, it can be used in both water treatment, wastewater treatment, industrial treatment. We've talked about lime soda ash softening. We can use ion exchange to remove calcium and magnesium. Those of you that have a water softener at home, that is an ion exchange unit. We can also use it for demineralization. So we can remove more minerals than just calcium and magnesium. At the MSU power plant, they use both ion exchange, cation exchange and anion exchange. So they're removing calcium and magnesium and other cations on the cation exchange column. And then they are removing anions such as sulfate, chloride, nitrate in the anion column. So what they're doing is they're replacing these anions with either H plus or OH minus. We can also use it for ammonia removal. So in this case, we're looking at removal of ammonium ion, and that would be done on a cation exchange column. We can remove metals. We need to know the charge of those metals. So for instance, if we're looking at removing manganese, we need to know it's either manganese 2, manganese 4, but what state is it in? Okay. Is it as a hydroxyl ion? So for instance, arsenic is as arsenite or arsenate. So the ionic form plays a significant role. And then we can also look at removal of radionuclides from americesium to plutonium, etc. So again, we need to know something about the redox state of that ion. In terms of removal, ion exchange is what we call an exchange process, and you can see it here. So what we have is we have sodium ions, and those ions then will replace a H plus, so that H plus is released and the sodium is adsorbed. If we had calcium, 2 plus, now what happens is if this is exchanged, that will replace 2 protons so that we can maintain charge balance. So here, we're going to replace those, and we would have a calcium replacing those 2 hydrogens. These reactions can occur on a synthetic polymeric material, looks like you see on the right-hand side. So these are polymeric beads. They can also be a zeolite material. So this is a naturally occurring material. This is ground here. And these typically have a structure something similar to the sodium, aluminum, and a silica base. And this is just one formula. Okay, and these sodiums could be sodium, they could also be potassium, they could be calcium, they could be magnesium. Okay, they can be a clay material. So clays are actually very good at ion exchange, acting as an ion exchange material. So for instance, kaolinite, which is a type of clay, is Al2 SiO5 OH4. So it's the OH group that is exchanged. Cliniptolite, another clay material, can be a combination of sodium, potassium, calcium. The ratio depends on the forms. With a aluminum, I'm not going to write this one down. It's basically an aluminum a silica oxide. Okay, and I will fill that in later because I realized I have it in my notes incorrectly. But you have these different species. Like I said, they can be soils, they can be synthetic polymers, like you see here. This is you see the polymeric structure here. We often talk about cross-linking, and you can see the cross-linking here. So you see you've got a benzene ring, and then you have multiple carbons that are associated with the benzene ring. So you've got a carbon-carbon bond here, and this creates this kind of structure that you see here, and this cross-linking. And this can be, the degree of cross-linking can vary, and that changes the behavior of the ion exchange resin material. So materials that have a higher degree of cross-linking are not able to withstand what we call a swelling pressure. So they tend to be more fragile than a material with less cross-linking. Now you can see here, in this case, this resin is in a sodium form. So we'll refer to this as a sodium form. That sodium can be exchanged. And in this case, if it's calcium, we have two sodiums that are exchanged for one calcium. In this case, we have a resin in the chloride form, and that chloride can be exchanged, for instance, for a nitrate. So it's exchanged on an ion basis, but we always have to maintain charge. So it's really, when we talk about ion exchange materials, we will talk about equivalence. We can also use milligrams per liter as calcium carbonate. We need to maintain charge balance. We can have resins that are strong acid, weak acid, strong base, weak base. What that pertains to here is, this is sulfite, it's a strong acid. Here we have acetic acid, it's a weak acid. So that's what we talk when we talk about strong acid versus weak acid. Now, strong acid is going to want to keep the sodium more than a weak acid will. The strong acid, have a wide pH range they can operate at. However, regeneration is less effective, typically about 30 to 50%. And when we talk about regeneration, those of you that have a softening unit in the home, you operate the unit typically in a sodium mode. You're exchanging the sodium for calcium. And then when the ion exchange capacity is reached, or what we call exhausted, then what you need to do is you need to shift the equilibrium back. Typically use a salt solution. So we use, in this case, we'd use a concentrated salt solution to shift that equilibrium back so that the resin is restored in a sodium form. With a weak acid, the way that this is shown here, this could also be in a sodium form, but it's shown in a hydrogen form. Here, regeneration is much more effective, and it can approach 100%. So we can get essentially complete regeneration. The problem here is we can operate these at only if the pH is greater than 7. So most effective if that pH is greater than 7. Similarly, strong base resins can be operated at a wider pH range, but again, regeneration is effective only at about 30 to 50%. And then weak base resins really react more by adsorption than by ion exchange. And again, regeneration can be achieved at about 100%. So that gives you some sense of the different types of resins and how they typically operate. Now, resins will prefer one ion over another. And these are typical rules here. What you see is one, ions of a higher valence are preferred over those with a lower valence state. So for example, iron is preferred over magnesium, over sodium. Phosphate is preferred over sulfate, over nitrate. Aluminum, 3+, is preferred over calcium, which is preferred over sodium. Now, these reactions are actually important to think about when, especially in a soil system, and I'll answer Austin's question in a second, but in a soil system where you're applying water from, for instance, manure treatment that has a high phosphate, what happens then is if you have phosphate and nitrate, notice the phosphate is preferred over the nitrate. As a result, the phosphate is adsorbed or exchanged to the soil material, resulting in the release of nitrate. And that ends up resulting in the contamination of groundwater with nitrate. So in an agricultural region, rarely will you see groundwaters contaminated with phosphate. On the other hand, you will see groundwaters contaminated with nitrate. So rarely phosphate, but you will see nitrate contamination. To answer Austin's question regarding is the softening salt direct, so basically issue about the softening salt. The softening salt that you apply to a home water softener is regenerating the resin. So it's shifting the equilibrium from the calcium and magnesium on the resin, releasing the calcium and magnesium into that waste stream and then restoring the resin in the sodium mode so that it can operate effectively again. Another issue with selectivity is that it increases with decreasing hydrated radius and increasing atomic number. So if we look at the periodic table, we have hydrogen, lithium, sodium, potassium, rubidium, cesium, and franconium. Okay, so those are alkali elements. As we move down the periodic table, the radius increases. However, the hydrated radius, so the radius of that ion in water, actually decreases as we move down. Okay? So it's increasing here, but it's increasing. The hydrated radius is the exact opposite. So the hydrated radius of hydrogen is greater than that of sodium. And if you remember, I mentioned that swelling pressure. So that hydrated radius results in the presence of these ions result in a swelling pressure. And if the swelling pressure is too great, it can actually degrade the polymer from a physical perspective. So in terms of selectivity, then, so if you look here, potassium is preferred over sodium, is preferred over lithium. Okay, so it's the opposite. Okay, as we move, they're preferred as we moved up the periodic table. So calcium is preferred over magnesium, is preferred over beryllium. And these are important when you're looking at your composition of the water in terms of really the competitive reactions. And the other thing is that selectivity tends to decrease with increasing cross-linking. So if you're simply looking at two resins, so if you're looking at especially larger molecules, the selectivity is going to be less on a resin with high degree of cross-linking. So it's important to understand this so you can get a sense of which resins are most appropriate. Selectivity plays a significant role in the operation of the resin. So if you have a resin with a high affinity for that ion, and if we plot C effluent versus the volume that we treat, we get a breakthrough curve. And we talked about the concentration of breakthrough. The theory is identical to what we used for adsorption. And we have C exhaustion. If we have, and I'll change color here. If, on the other hand, we have a resin with a very sharp breakthrough curve, here's CB here, we more effectively use the resin before we regenerate. Now, this results in a shorter column. It means we can get a greater flow through before we actually have to regenerate. And when we have a high affinity, we have this sharper breakthrough. The problem is we're going to need more regenerant to regenerate. So the regeneration is more difficult with a ion exchange set resin that has a high degree of selectivity. Now let's think where would we want a resin to have a very high degree of selectivity? And what types of situations would we want the resin, would we want to maximize the selectivity? Think about the PFAS chemicals. One of the challenges with PFAS, we don't have a good means of degrading PFAS chemicals. We can incinerate, but we have to incinerate at above 1,000 degrees C to destroy the PFAS chemicals, the carbon fluorine bond. So if we use an ion exchange system to remove PFAS chemicals, we now have the PFAS chemical on the resin. If we regenerate it, where is the PFAS chemical? So here's our ion exchange resin. We'll run through it in. So we load the column with the PFAS chemical. Now we have PFAS on the resin. And hopefully we have clean water. When we regenerate, so now let's regenerate the column. Where's the PFAS?
Is it going into the effluent?
Exactly, it's right here in my regenerant stream. Now what do?
I still need to figure out how to dispose of it.
Exactly. Now I'm back to having an aqueous solution that I still have to dispose of. It may be a more concentrated solution, but I still have an aqueous solution that I have to dispose of. So with a material like that, it may make sense not to regenerate, to simply exhaust the resin. You've now got your material on a solid support that potentially then you can solidify and dispose of. And this is what we do with radionuclides, because we can't destroy radionuclides. So with radionuclides, and we could look at the same type of approach with PFAS, what we use is this merry-go-round system. So we have column 1 here. We load up column 1. We run that not to breakthrough, but we run that to exhaustion. But we also have another column here that's essentially a polishing step. And we can have a third column here. So this is 2, and this is 3. So hopefully by the time we get through 3, we essentially have captured the radionuclides. When this reaches exhaustion, what we then want to do is we take this offline. We can solidify that material. This column becomes 1, this column becomes 2, and now we add a clean column that is 3. And then we continue to operate that until what is now column 1 becomes exhausted, and we keep with this approach. So basically what we do then is we can take that material from column 1. We can solidify it. We can solidify it by a number of means, including solidifying it in a polymeric material, and then they essentially extrude it into kind of like polymeric sausages with the radionuclides in this incorporated into this material. You can use concrete. You can use asphalt type materials. So there's multiple ways to do this. But basically what you're doing is you're creating a solid support. And if it's radionuclides, then you're disposing of it either in a high level rad waste facility or a low level rad waste facility, depending on the radiation level. So that kind of gives you there you really want a resin that is highly selective. And typically for these radionuclides, these are very expensive resins. So we want to maximize the exchange capacity, and we don't regenerate, because otherwise we end up with the radionuclide back in aqueous systems. Same thing is happening with activated carbon with PFAS chemicals. Problem we have with regenerating activated carbon, we can regenerate with steam, but if we regenerate it with steam, now we have PFAS chemicals in that gas stream. Now what do? Incineration is about the only thing we can do, but we need an incinerator that operates at over 1,000 degrees C. And for instance, in Michigan, there isn't one, which is why it's big. If you look up PFAS, fire exchange, the firefighting foam, you'll see that most of that was actually exported from the state. And the reason is because there's nothing we can do. We can store it. We can't dispose of it. We can't treat it because we don't have a way of doing so in the state. And what they ended up doing was incinerating that firefighting foam that contained PFAS, but they had to do it out of state because they had to do it at a facility that could incinerate at greater than 1,000 degrees C. So any questions about kind of the operation of how this? When we talk about ion exchange resins, we talk about capacity of those resins, and we talk about total capacity and operating capacity. Total capacity is a measure of, it's a theoretical value. If we know how many exchange sites we have on the resin, we can then determine the total of theoretical capacity that can be exchanged. And this is typically in milliequivalents, and it's milliequivalents of whatever ion you're exchanging. And this is per liter of resin, or in this case, grams of resin. So this is milliequivalents of the exchange ion per liter volume or mass of the resin. The operating capacity, you can think of that as the useful capacity or the actual capacity, and that is what we can actually achieve. So in theory, maybe we could, let's say, remove 1,000 milliequivalents per liter. But when we actually operate the system, we only find that we can remove 600. And that's going to depend on a number of factors, including, we talked about the selectivity. So which ions are you removing? And the competition. So it's really what other ions do you have in solution? It's also a function of the flow rate through the column. It's a function of the bed depth. And think there, we talked about the number of transfer units. So bed depth is related to the number of transfer units. The more transfer units, the better removal. Ion exchange, the exchange ion size, that's going to affect your selectivity coefficient. How well did you regenerate that resin? If you don't do a good job at regenerating the resin, then you still have, for instance, if you have a home water softener, your home water softener starts in a sodium mode. You replace that with calcium, and then you regenerate to go back to that sodium mode. And if you don't effectively regenerate, you have fewer sites available for additional removal of calcium. Temperature also plays a role. So if you increase temperature, the pressure drop across the resin decreases, and that's because the pressure drop is directly proportional to the viscosity of the liquid. And we know that viscosity decreases as temperature increases. Temperature also decreases expansion during backwashing. With an ion exchange resin in a column, we operate these very similar to the way that we operated our granular media filtration systems. So we will, just as we, in the filtration, when we backwashed, we wanted to expand the filter bed, we do the same thing in an ion exchange system. So during backwashing, we will fluidize the bed, and that will help release any solid particles that were captured. It also allows for better regeneration. And backwashing can also help with removal of organics. And finally, the desired quality of the product water affects how much water we can treat to the point where we have to regenerate. This is just a schematic trying to show essentially what I've been talking about. So for instance, in a softening process, you start with a water containing calcium and magnesium. You start with a resin in a sodium mode. So what happens is as we pass the water through, the softened water contains sodium and the resins now contain calcium. So the sodium is released and is exchanged for calcium. So when we regenerate, we'll start with a concentrated sodium chloride solution. And what we will then do is now we start with calcium or magnesium. We're going to release those and replace that with sodium. And we again still have to maintain a charge balance. We could also regenerate with hydrochloric acid if we wanted, and if we regenerated with hydrochloric acid, my resins would have what cation? We'd be replacing the calcium with what?
Would be 2 hydrogens.
Exactly, it would be 2 hydrogens. Okay, so now it would be in a hydrogen mode. Why don't we do that in home water softeners? It's what we do at the MSU power plant right here. Why don't we do that at home?
Is it a safety concern?
Safety concern. You need hydrochloric acid, so it's a lot safer to have a sodium chloride solution than it is to have a concentrated hydrochloric acid solution. The other reason is you'd be adding hydrogen ions, and that's going to lower your pH. So if you don't have sufficient alkalinity in order to buffer the system, you're going to end up with a treated water with a low pH, and then you have the potential. So we could, but we have issues with safety, and we have issues with decreasing the pH and resulting in increased corrosion, which also can be a safety concern because of the release of metals into the water. The ion exchange system operates the same way as your adsorption system. In fact, this is the exact same figure that I used for adsorption. With adsorption, we talked about an adsorption zone. With ion exchange, we talk about an exchange zone, exactly identical. So if this is our exchange zone, at the bottom of that exchange zone, this concentration is the exhaust concentration. Now my exchange zone has moved down the column. So if I had a sampling port here, the concentration at this point would be what? It would be my C sub B, or my exhausted. Okay, 95% of Cn. Same thing. My exchange zone has moved down the column. So now, if I have a sampling port there, what's the concentration?
Exhaustion.
C sub B. And you can see the same thing here. So we have a breakthrough curve. Okay. Now, here, you can see this is our breakthrough. This is the portion of the capacity that we're actually using. This portion here is what we can't use. So if we take this mass here, so we can, if we multiply concentration times volume, we have mass. So this is the mass to breakthrough over the total mass removed to exhaustion. This gives us a sense of the efficiency. If we have a very sharp breakthrough, so let's just, I'm going to change. So now we have a very sharp breakthrough that looks more like this. Now, this is that mass. Okay, we're still using the same. This is still the mass to breakthrough. This is that kind of mass we can't use. So which one is more efficient? I'll call this number 1 or number 2. Which is a more efficient use of the resin capacity? 1 or 2? 2. Okay. We've essentially, think about it, we've wasted. This green area here we can't use. Okay? So it's essentially a waste. Okay? So 2 is a more efficient use of the resin. In terms of operation, this just gives you a sense of what an ion exchange looks like. If you have one at home and you actually pulled it apart, this is what it would look like. You have a manifold at the top, and water flows from that manifold through the resin bed, and then is collected at the bottom, and that is what's distributed through the home. When you're backwashing, you're doing the opposite. So backwashing, you have water flowing. So we backwash, regenerate, the water flows from the bottom, you fluidize the bed, flows out the top, and that would go to a waste stream, typically the sewer. And if you recall, Greg Tutara talked about in his video that he did for us, where they said that they were deep injecting into a deep well. So they the water, the treated effluent from their wastewater treatment plant, they were discharging that not into a body of water, but they were discharging into a deep well. And he said that they stopped doing that because of the softening units. Anybody catch that? So what was the problem? And he said what the contamination was. He said that it was salt contamination. So what's happening?
You're pumping the salt contaminated water back into the aquifer.
Exactly.
And altering its ion content.
That's exactly what was happening. Okay. So they stopped doing it because there were most of the community, because they didn't have centralized softening, much of the community had water softeners in the home. That regenerate solution has a high chloride concentration, was then being discharged to the sewer system, and there was sufficient number of water softeners to actually change the ionic composition of the wastewater, and therefore change the ionic composition of the groundwater and the aquifer. It's one of the major problems with water softeners, is the issue with what do we do with this regenerate solution. So the last slide that I'll show today is question, when do we use lime softening over, when do we use ion exchange over lime soda ash softening? If it was a normal year, we would visit the Williamston water treatment plant. It's about a 2 million gallon a day plant. They have ion exchange versus East Lansing, which is about a 10 mgd plant, or Lansing, which is about 40 mgd, where they have lime soda ash softening. Typically with a smaller plant, you have fewer operators to operate the plant. You can operate a ion exchange system with fewer personnel than you can a lime soda ash softening. You also don't have, you have your regenerate solution, but you don't have the sludge that you have to deal with. Typically, if your raw water contains low color and turbidity, so you don't need pretreatment, and this is the case in Williamston, you can use ion exchange. Typically, if you have a high amount of non-carbonate hardness, then ion exchange is preferred over lime soda ash softening, or if you have very variable hardness levels, so that process control is difficult with lime soda ash softening, ion exchange is better there. I'm going to end there. The next couple slides really just talk about service flow rates. On Monday, what we will do is we'll go through example 1, and we'll use the design criteria that I just flipped past. I have posted a PDF and a Word file for example 1. So on Monday, what we'll do is we'll go through this example. We'll actually design a softening ion exchange system, and we'll look at the various different parameters, and we'll actually calculate how long we have to backwash, how long we have to regenerate, et cetera. So we'll design the entire system on Monday. So you'll want to download either the PDF or the Word file for the example, and we'll go through that on Monday. Any questions? And I apologize for going over a couple. If there's no questions, I will open up the participation question in a few minutes, and I will have a wonderful weekend, and I'll see you on Monday.